In this lesson, we're going to learn how to graph quadratic equations. There are three different types of quadratic functions that we're going to learn how to graph. And the first one is graphing from vertex form, which should look really familiar. One way to graph from vertex form is to use parent function transformations. So you can continue to graph that way. I'm going to show you another way to graph. If transformations was something you struggled with, there's an alternate way to get it graphed. First thing we need to identify is the vertex. When we did transformations, we called that the critical point. The vertex is the turning point for the graph. So when we look at this, we can see that we have a shift right 4, so that's the x-coordinate of our vertex or critical point, and up 5, so that is the y-coordinate of our critical point or vertex. We can also recognize that this opens down. It is a vertical reflection, so make sure that your equation matches your graph. The axis of symmetry is a line that the graph reflects across. So think about parabolas. They're a U-shaped function, and if you place a vertical line through the vertex, you will get a mirror image of the graph. So the axis of symmetry is the vertical equation x equals 4. It will always be the x-coordinate of the vertex for your axis of symmetry. So the alternate way to get this graphed is to use a t-chart. Once you identify the vertex or the critical point, you can substitute two values less than the x-coordinate of the vertex into the function and two values greater than the x-coordinate of the vertex into the function. So the x-coordinate of our vertex was 4, and we know the y value was 5. So for our t-chart, we would substitute two values smaller than the x-coordinate, as well as two values larger than the x-coordinate into our function. So taking a look at our equation, if we substitute 2 in for x, and then we solve. Remembering order of operations, we're going to simplify what's inside the parentheses first. Then we are going to square. Notice the negative on the outside does not cancel the negative on the inside because we are following order of operations. So we get -4 plus 5 is 1. So that's the y-coordinate for an ordered pair of 2. If we substitute 3 into the function, we get a y value of 4. If we substitute 5 into the function, we get a y value of 4. And substituting 6, we get a y value of 1. Again, keeping track of the order of operations. To save a little bit of time, I jumped ahead instead of showing all of my work on those. So when you graph this, start with that critical point. I'm going to count each of these as 2, so you can follow me when I'm graphing. So going to 4, 5, and then just plotting those other ordered pairs that we found. Again, if you're comfortable with transformations, you can use the parent function t-chart instead of substituting values into the function that you're given. Last piece, we're going to look at domain and range for this function. Domain for any quadratic function is all real numbers. The range for a quadratic function will be greater than or equal to or less than or equal to the y value of the critical point. The vertex of the quadratic function is where the graph changes, in our case, from increasing to decreasing. So our y values are all less than or equal to the y value of our critical point, in this case 5. If your graph opens up, your range will be y is greater than or equal to the y-coordinate of your vertex. This one, instead of graphing, we're just going to find all of that important information. So first of all, determining the vertex. This one is in vertex form. If you expand this, you would have x minus 0 squared. So then you can recognize that our vertex, or critical point, is 0, -3. All we had was a vertical shift down 3. We did not have a horizontal shift on this one. We also have a vertical stretch of 2 if you would use parent functions and transformations to graph this. Axis of symmetry is always x equals the x-coordinate of your vertex. Domain for quadratic functions is always all real numbers. And the range, we need to determine if our graph is opening up or down. In this case, we have a positive coefficient, which means there was not a reflection. So it is opening up. So we have y is greater than or equal to -3, the y coordinate of our vertex. Real quickly, I forgot to show you the axis of symmetry on the graph. The vertical line x equals 4, if you sketch that on the graph, goes right through that vertex and again creates a mirror image of the graph. Just cut that out.